Alright, so what I'm going to talk about today is joint work with Eric Laszlo and David Truman. So we posted a paper on the archive about a couple of months ago. I encourage you to check it out if you'd be interested in what I'm going to say. So I would like to start with an abstract of our project and then move to two very concrete examples so that we get a better idea of what's going on. The abstract is the following. So in our project, what we do is construct a model for the Sibilla category on a puncture Riemann surface. Sigma is a puncture Riemann surface. I've called this model Cp and sigma. So this is a digit category which is conjecturally quasi-equivalent to the Sibilla category, but we haven't proved the conjecture yet. And the next thing we do is that we use this model to prove a homological mirror symmetry statement. So let me remind you, homological mirror symmetry is a conjecture that Kotsievich put forward, I think, in '94. And let me remind you what is the setup. So we are supposed to be given an algebraic variety X, a symplectic manifold X twiddle, and if X and X twiddle are mirror partners, we are supposed to be able to prove that the derived category of covariant sheet over X is quasi-equivalent to the Sibilla category. So what we have in our project is that for us X is a degeneration of an elliptic curve. So it's what we call a necklace of P1s. Let me draw a picture. So we will have a chain of P1s glued in this way, and the mirror on the symplectic side will be a puncture torus. So let me call this Xn, where n is the number of components. This is going to be X twiddle n, where n is the number of punctures. And what we prove in our paper is that perf Xn is quasi-equivalent to Cpm X twiddle n. So if you believe, as we do, that this is quasi-equivalent to the Sibilla category of this puncture torus, we obtain homological mirror symmetry. Let me comment on perf Xn. So perf is a subcategory of the full derived category of covariant sheets. Is a better behaved substitute that we use because Xn is singular. It's simply the category of complexes of vector bundles, rough. So this is the kind of the abstract of my talk. The first example I want to discuss with you is a kind of a toy example. It's just homological mirror symmetry for P1. So this will kind of motivate the story I'm going to tell you next. So the way I'm going to obtain this homological mirror symmetry statement will be composing a chain of equivalence of categories. So the first category we're going to consider lives in the algebra of geometric work, and is simply the derived category of covariant sheets over P1. The second category lives in the world of representation theory, and is the category of representations of this field. Okay, we have two vertices and two arrows between them. The equivalence between these two guys is a famous theorem of Benenson at the end of the 70s. Which prove it more generally for projective spaces. And the functor here is very simple. Let not me write it down, but it's very simple to understand what's going on. The third category lives in yet a different world, which is the world of shift theory. So this is in turn equivalent to the category of constructible sheets over S1 stratified by a point. So what is a constructible sheet? Constructible sheet is a sheet of complex vector spaces, finite-dimensional complex vector spaces, which is constant when restricted on the two sets of the stratification. So when restricted on the point and then on the complement of the point, is quite easy to convince oneself that the datum of such a sheet is exactly encoded in a representation of this figure. What we will have, we will take its stock at 0, its stock at F1, and then we will have two restriction maps. Okay? So these are the first three categories. Finally, the fourth category, which will appear unfortunately on that board, is lives in the world of symplectic geometry. How do I erase what I do? Sorry. Oh, great. Thanks so much. All right. So the fourth category, as I was telling you, lives in the world of symplectic geometry, and so we make contact finally with homological mirror symmetry. And so let me call it the Fukaya category of Tristan S1 with respect to lambda. I'll explain all these objects, what are all these objects in a second. So Tristan S1 is simply a cylinder. Lambda is a subspace of this guy, which is made up of the zero section and the cotangent fiber at 0. Okay? So what do I mean by this expression? I'm looking at exact Lagrangians, which are in an appropriate sense asymptotic to this shape that lives in this S1. So let me draw one for you, if I manage. So they can go like this, they can wrap around perhaps a couple of times, but then they need to be asymptotic to this shape. Is it clear? Are there questions about that? Right? Okay, so the equivalence between that category over there and this category comes from theorems of Nadler and Zaslow and Nadler, which give us a way exactly of understanding the Fukaya category in terms of constructible sheet. The Fukaya category of a cotangent bundle, in this case we have this S1, in terms of constructible sheets over the base network. This is exactly what's going on here. So, what? Nadler, Zaslow, Nadler? Yeah, two papers. Great. So now if we read this chain of equivalences, starting from here and ending there, we start from the derived category of coherent sheets, and we land with the Fukaya category of Tristan S1, and so we obtain a homological mirror symmetry kind of statement. Let me convince you that this chain of equivalences doesn't realize any equivalence, any random equivalence. Actually, it fits in very well with our intuition of how mirror symmetry should work, in particular in the SOC picture. So let me just say a couple of words about this, very briefly. And the fact that this is the case, I'll write a couple of names on the board. So the fact that this equivalence that I just described does fit in with the SOC picture of homological mirror symmetry. It's proved by Bohr-Fang for projective spaces, and then there is generalization by Fang, Liu, Ruhmann, and Zaslow for Tauri varieties. So what's going on? We have P1 over here. In the SOC picture of mirror symmetry, we are supposed to find the torus vibration on this guy. So in this case, this will be given simply by the moment map. I'm secretly removing 0 to infinity, but let's not worry about this. Then I'm supposed to dualize fiber-wise this torus vibration. What I see on the other side is something that looks roughly like this. So as the circles become smaller and smaller on the left-hand side, they will explode in size on the right-hand side. And further, so this is XYZ. Further, SOZ gives us a prescription given a line bundle on the left-hand side, let me call it L, to draw, gives us a description for drawing a Lagrangian on the other side, and this Lagrangian will look exactly something like this. So, something along these lines, and what was proved is precisely that this chain of equivalences reproduces the SOZ picture of homological mirror symmetry, and so it's legitimately a mirror symmetry state. So this is the case of P1. Now I want to move to our project. First, let me single out a couple of the features that make this example so appealing to me. Is that first, we were able to encode the algebraic geometry of P1 in an entirely combinatorial object, which is this lambda over here. So lambda is this guy, a skeleton. Lambda is simply a graph, simply a four-valent graph, and all we really needed to do to set up this chain of equivalence was knowing its, let me say, its combinatorial type. So we encoded the algebraic geometry of P1 in this combinatorial object, this graph, which was this subspace living in this S1. And the second thing is that dealing with the Fukaya category was especially easy because we could use the Nader-Zaslow dictionary to translate the Fukaya category in terms of constructible sheets, which are much more amenable to computation, let me say like this. Okay? So these are the two features that I would like to explore in the next example, in the necklace of P1 example. Okay? Are there questions about this? All right, so let me move to the next example. So again, for concreteness, I'll focus on one specific, what I call necklace of P1, and it is this guy. So we have a P1 over here. And we have a P1 over here. So two components is what is called by some people a banana curve. And I'm going to explain to you how we can obtain a homological mirror symmetry statement for this guy. So the first question is, what is going to be the combinatorial object that allow me to encode this configuration? And I explained to you before that somehow this copy of P1 contributes this guy, this lambda. This other copy of P1 contributes the same thing. So it's pretty natural to guess that the graph, right, the combinatorial object that is going to encode this configuration will be obtained by joining together the upward pointing ray and the downward pointing ray. Okay? So this is our first guess that the combinatorial object is this guy, is this graph. Right? These are actually ribbon graphs because they come with an embedding in a surface, in a sense. Okay, but let's not worry about this, it's just a technical point. So this is our gamma. Note that gamma doesn't live anymore in a cotangent bundle. Gamma lives in a torus minus 2 punctures. Let me draw it for you. So this is gamma, and gamma is over here, and you can convince yourself it's really just a deformational tract of a torus with 2 punctures. Okay? So what we would like to add is being able to describe the Fukaya category of this torus with 2 punctures in terms of some kind of sheet theory. This is exactly one of the features I highlighted in the previous case, and so one guess could be whether we look at constructible sheets over this graph of this one-dimensional space, this doesn't quite work. What works, and what is described in the paper, is that we can define a sheaf of digit categories, which we call CPM, so such that locally CPM is given by a category of constructible sheets. So what do I mean by this? Let me draw again my gamma. So here is gamma. We can decompose this gamma into open sets. For instance, this is, let me call this U1. This other open set is U2. And CPM U1, so CPM is a sheet over this topological space. So we can compute its section of U1. This is going to be sheets on S1 stratified by a point. So it's going to be exactly a category of constructible sheets, and the same, of course, is true for U2. Okay, so that's it here. So our conjecture is that the global section. Let me write it for you. So conjecture, CPM gamma is quasi-equivalent to the Fukaya category of the torus minus the points, and further we prove that CPM gamma, so this is a theorem, CPM gamma, so the global section of the sheet, are quasi-equivalent to perf X, where X is the banana curve. All right, so let me comment on a couple of things. So the first thing is that we can actually define CPM for any graph of this sort, for any ribbon graph, and so not just for a puncture torus, but for a puncture Riemann surface of any genus. And so this allows us to construct a model for the Fukaya category of a puncture Riemann curve of any genus. I insisted on this example because it's the one that is most relevant for topological mirror symmetry. For this statement over here. Let me put this in quotes. And the last thing I would like to do for you is convince you that this equivalence that was motivated essentially by looking at the combinatorics of this graph actually again fits very well within the SYZ picture of typoality. So let me just draw a picture for you, and this will be the last thing that I'm going to tell you today. So the heuristics that justifies that the mirror of a banana curve is a torus minus 2 points, again comes from SYZ. So here is my banana curve. I have a fibration in S1s, which has two singularities, over here and over here. So the preimage on all these points will be an S1, but will be just a point over these special points in the base. And when we typalize, we are supposed to consider fiber-wise circles that have the inverse size of these circles. So what we get, if you believe that we should consider the dual of a circle of radius 0, a circle with infinite radius will be exactly a torus with two punctures corresponding to these 2 points. I don't know if this is making sense. We can talk more about this if you're curious. So that's all. Thanks a lot.